All right, we're live. Good afternoon, everybody. Thank you so much for joining us. My name is Manan Banerjee. I'm a robotics technical specialist with Cross Robotic. We're based in Belmont, North Carolina. I am at our headquarters in Greensboro, North Carolina. uh, I feel like I know why most of you are here. It's because you may have an application or you're just interested in the technology of bin picking. So what we're going to talk about today is bin picking and you. This is roughly how it's going to be laid out. First, I'll go over who Cross Robotics is. What is bin picking? What does it involve? How the technology provides ROI, which is going to be important because, as I'll say many, many times, it's not the cheapest or the easiest way to present your parts to a robot. When you should consider, when not to consider. Sweet spots, kind of indicators, things that bin picking kind of jibes really well with. What do we have in place that might be able to help you? We've put together kind of a solution with a cobot and a bin picking camera. And then right after that, we'll do a live demo and take any questions. I will note, just as kind of on the logistics side, I will pause here and there for questions. I'll take, let's say, one question at a time every now and then before we move on. If you have a more involved question, we can save it to the end. The presentation is going to take about 45 minutes, and then I'll stay for as long as you guys are asking questions. So without any further ado, who is Cross Robotics? Well, obviously we do robots. We can provide robots, program them, integrate them. We can provide end effector components, design, general componentry, safety, area scanners, light curtains, extruded aluminum workstations, just mechanical design, a la carte services and support. We want you to consider us as an extension of your engineering department. So if you have a robotic application or even part of one that you want our help with, we will be as involved as you'll let us be. At the end of the day, our focus is to help you achieve your business goals by focusing on your most challenging applications. So what is bin picking? Well, spoiler alert, kind of, pretty much what it sounds like. It's you're picking parts out of a bin. In a nutshell, you have a camera system, something to control the camera, and a robot. It doesn't actually need to be like a six-axis robot, but it helps because your parts can be oriented. But anyway, so you have a really, really sophisticated vision system, see the contents of the bin, and pick the best candidate to pick up. Imagine something like you guys have played those rigged claw machine games at the arcade. The process is kind of similar. You kind of scope out what's in front of you. You can't predict anything, but you can see what's in part of you, kind of determine what you're going to go for, and then guide an end effector and do some kind of approach and grab process. The only difference is a robot isn't clearly rigged in every way, and it just doesn't just arbitrarily drop parts because it was designed to. Kind of the opposite. So anyway, bin picking is really easy for people. In fact, any one of you watching, I could probably blindfold you, put you in front of this bin, and without even telling you what the parts are, you could probably pick one part out of the bin, no problem. It's actually so easy. If I then said, hey, great job, you're going to do that for 8 straight hours and you get an hour for lunch, you would probably wince pretty hard at the prospect of doing that. We'll talk about the ramifications of that in a little later, but bottom line is it's really easy for people, has been really difficult to robustly automate. And before we get into why it's so difficult, let's talk about part presentation in general. So if any of you guys are in automation, either designing machinery or implementing automation, you know that part presentation is a major, major part of any automation effort, right? How are you going to present one part at a time, predictably, repeatably, to a robot, work cell, conveyor belt, camera, whatever, right? So a lot of time, effort, and money, probably most importantly, goes into this. And bin picking is just one of several ways to handle this. What other ways are there? Well, I've listed a couple. Nested trays, kind of like an egg carton or some kind of jig or fixturing. Bowl feeding for less fixturing required. but still pretty fast cycle times. 2D vision, as you can see there, they're parts just laid out on a table. You're fixed in your orientation. You just need a camera to tell you X and Y, which is pretty straightforward as far as vision goes. And then you have flexible feeding, which some of you guys may be familiar with, but basically it's now your parts are on a table, but you have the ability to shake the table, so if your camera doesn't find parts, you can kind of agitate them a little bit to find something, create basically a new layout for your camera. Again, bin picking is one of several ways to handle this. I would encourage most customers to investigate at least these other ways of doing it, because they're more straightforward and they can be cheaper than bin picking. This next slide's, okay, so you're going to see a series of radar graphs here, and this is what each of them looks like, okay? So the more the radar graph is full to the outside, so the closer to the outside it is, the better it is, right? So initial investment, maxed out means that it's not too demanding as far as capital expenditure. Expertise needed, maxed out means you don't need that much expertise. So think of it in terms of better or worse, not in terms of some kind of absolute value, right? So if we look at kind of the different ways of doing it, the main thing I want you guys to take away from this is look at the differences between mechanical singulation. I'm pointing at something you guys can't see, I know that. The difference between mechanical singulation and 3D unstructured bin picking, meaning kind of like what we have here, just parts dumped in a bin, no staging whatsoever, is that bin picking maxes out on capability. You can handle multiple parts. You don't need to worry about presenting the parts, in a very specific way. But mechanical singulation is better in all the other ways, right? So you don't need a lot of expertise. Like, imagine designing an egg carton. Apologies if anyone out there designs egg cartons. I don't know what goes into it, but imagine designing an egg carton. Seems pretty straightforward. Ease of use, yeah, you put the eggs in them or your parts. Initial investment, probably a pretty cheap way to fixture your parts, right? Bin picking is none of those. It's much more sophisticated. You need more expertise. You need to be savvy with not only robotics, or I say you, whoever's implementing the bin picking system needs to be savvy with not only robotics, but also machine vision, and also how to handle almost total unpredictability with your parts, right? So, like I said, what's so difficult about it? You can't predict. On a technical side, imagine this is your part, this is what we have. With fixturing, you put this in a fixture, and you know exactly where that part is in all degrees of freedom, right? If I just throw it into a bin, I can't predict any of those degrees of freedom. So I need the camera to look at what's going on there, do a bunch of math, and basically pick the best candidate. Now, on top of just how your part's oriented, it can be blocked by other parts. It can be entangled with other parts. Your end effector might be such on your robot that you're going to collide with the bin or other parts. Because you can't predict how your parts are going to be oriented, you also can't really predict how your robot's going to end up, right? So without a lot of testing, you can't say for sure that the robot's not going to reach some ridiculous singularity in trying to reach a part. So that, kind of in a nutshell, again, that's what's so difficult about bin picking. I'm going to pause here real quick just to take a question, if anyone has one at this point.
Yeah, Manan, we've got a good question here. How many different parts can a system like this handle?
Oh, great question. Thank you to whoever asked that. So one of the really nice things about bin picking is it can handle multiple parts. A fixture is designed for one part. A bin picking camera, you tell it, as long as you have a 3D file of your part, the camera can handle way more than one. Now, what's the upper limit? Honestly, from the technical side, it's probably limited by the storage space on the hard drive where you're storing all your programs and stuff. In a more practical sense, it really depends on your tolerance for sitting there programming. Because, like, for example, with this part, on top of the CAD model, I need to teach the camera how I can grab the part, right? So with this part, I believe we have about 18 or 20 different approaches set. So each of these tabs, you can see it. This tab can be approached, I think, 4 or 5 different ways. The way we have it, this one a little less. This side tab can be. So each part you want to teach, or each part you want to bin pick, requires kind of that level of attention. Pick up, the more time you're willing to spend on a part, the more successful your bin picking, or the more robust, I'll say, your bin picking deployment's going to be. So to answer your question, the upper limit is really how much effort are you willing to spend to iron all that out. So that's a great question. That's actually one of the main benefits of bin picking, so I appreciate that question. So if anyone else has any questions, just as a precursor to the rest of the presentation, I'm happy to take more questions at a time at the end of the presentation for anyone that has them. So for now, now that I've talked about how expensive and difficult bin picking is, how does our system with a cobot and a bin picking camera actually get you a return on that investment, right? Well, one of the major factors that any robotic deployment aims to mitigate is the labor cost, right? People require money to work, thankfully. But the average burden rate, so this is not, in an operator position, you have your hourly wage, right, which seems like a good way to sum up what that person costs. But the fully burdened rate, once you take into account training, onboarding, insurance, benefits, everything like that, the average, a good number for the average manufacturing facility, regardless of the skill level required for a position, which is interesting. This is the fully burdened rate, is between 22 to 25 an hour. It is a vast minority of customers that I've spoken with that go under 20, right? So really the true cost to have an operator for a position is in that ballpark. And like I said, many things contribute to this burden rate. Labor cost is the #1 metric. It's the #1 thing that my customers tell me they want to save on when we talk to them about robots. Now, I've mentioned an hourly rate. Especially on the labor cost, when you talk about multiple shifts, 2, 3 shifts, your ROI becomes very rapid. So on the labor cost side, if you run multiple shifts, definitely look at what your labor is costing you. Throughput, again, especially with multiple shifts, robots scale really well. The benefits of a robot scale really well as your volumes increase. Your customer says, hey, next year I want to produce 3 times this amount. Well, the easiest solution is to throw 3 times as many people at it, right? Hire as many people as you can to make increased capacity. But a robot doesn't take lunch breaks. It doesn't take any other kind of breaks. It doesn't complain, right? It never needs a day off. It doesn't need food. Doesn't need performance reviews. Well, I guess your engineers kind of review performance, but it's a different kind of review. Anyway, so what we found that even if we go in, evaluate an application, and the operator is just flying through this process, right? And you say, well, the robot cycle time is going to be a second or 2 slower than that, you know, maybe the ROI is not there. Yes, but when you account for the fact that the robot is a consistency powerhouse, over time, oftentimes even within a single shift, the robot has outpaced a human operator in terms of just cycles completed, right? The nice thing about bin picking specifically, if you have a bunch of changeovers, so say you need to fixture parts for the robot, that eats into your throughput, that contributes changeover time, right? With a bin picking system, when the bin is empty, remove it, put in a full bin. That's your changeover, right? And especially for high-value parts, the less time you can spend on non-value add touches to the part, the higher your ROI is going to be. We'll talk about high-value parts in a few minutes. Flexibility, again, with the great question earlier, a single bin picking system with a robot can handle not only multiple parts, processes as well. We'll talk about the multiple processes later. But mechanical fixturing and feeding, I won't say, it's not really right to say cannot do this, but it's much harder to do it with mechanical fixturing, especially with something like bowl feeding. Bowl feeding's great. It's a great technology. It's mature as a technology. But when you talk about processing the tooling costs required to handle multiple SKUs with a single bowl, for 2 or more SKUs, it becomes unfeasible very quickly, right? It gets much, much more expensive. 2D vision, again, another great technology, but it can depend on part symmetry quite a bit. So with our part here, this is a low voltage outlet box, by the way. You guys might have seen this if you worked on your house. With a 2D part, for 2D vision, this might not be a great candidate because there's so many different ways it can rest on a surface, right? So yeah, 2D vision can depend a lot on what your part actually looks like. The flexibility of process or of handling multiple processes specifically, it lets you bring automation to places where a single system might not be sufficient, right? So maybe you have throughput on this process, but every once in a while you run a different part through it. Well, if your tooling costs made that inaccessible for you, a bin picking system might be a great candidate. And I said the thing about non-value add touches, but every time you touch a part just to prepare it for a process, it's really hard to add value that way. So when you can take a single system and move it where it's needed, this has been one of the big things about cobots in the last couple of years, is that you can redeploy them, right? Your ROI tends to scale very rapidly. Changeover dictionary option, I'll actually save that for near the end if there's a question on it, because it's kind of easy to nerd out on that a little bit. But basically, our camera system stores all the possible orientations of your CAD file as a dictionary. So when it's presented with a new part orientation, it scrolls through that very quickly to find a match, rather than calculating the part every time. This, obviously, it minimizes changeover time. You need to, well, bin picking in general minimizes changeover time. You don't need to do part-specific fixturing anymore. And of course, this is probably obvious to you guys, less changeover time means more time in production. So the less time your system is sitting idle, the more time it's actually working for you. Retooling, so now you may be able to use, if you have parts in bins already, plastics people, I'm looking at you, you may be able to use the bins you already have, right? And especially for smaller shops or smaller businesses that don't have necessarily thousands and thousands of the same bin, replacing what bins you're using is, it's likely a lot cheaper than having 100 different types of tooling custom engineered and fabricated, right? This also, removing the tooling requirement also removes the need to create a new process to present the parts to the robot. If your system, again, redeployability, if the system is deployed to another process later, those parts probably don't need their own presentation method. It's just programming the robot and the camera at that point. So the tooling costs are significantly less on a bin picking system. Now, a major assumption of that is you don't need radically different end-of-arm tools on the robot, right? But talking about part presentation mostly there. And then retrofit, the cobot is meant, or cobots in general are meant for mimicking human capability, right? So this system, using a cobot and a camera that kind of identifies parts, using the same logic, for humans by humans, right? Uses the same logic that people do when scoping parts out in a bin. It's a really great way to kind of see what parts can be retrofitted. Instead of creating this whole new production line or a new process or having a custom machine built, you can just kind of say, okay, there's a person picking parts out of a bin all day, roll the system in right there and kind of bolt it on, like I say in the slide there. And especially with the collaborative robot, and now, again, if anyone's out there that I've come and spoken to you in person, I've probably kind of tongue-in-cheek said, hey, if you put a chainsaw on the end of the robot, it doesn't matter what type of robot it is, it's your application that's hazardous, not the fact that it's a robot, right? So with that disclaimer, in a lot of applications, you might not need any guarding at all. In other applications, you might need an area scanner or a light curtain just to detect human presence. In a lot of other applications, all you might need is an e-stop outside of the robot work envelope, right? But the collaborative robot, the robot being force and speed limited, mitigates the need. It solves a large part of your safety puzzle in just deploying a robot. And of course, the takeaway from this slide is that a retrofit, almost by definition, tends to cost less and deploys much more quickly than a full machine build or a production line setup, or a production line overhaul, sorry. And then value add. This is kind of intangible. If you're calculating ROI, you would probably have trouble putting this into a spreadsheet somewhere. But people, again, imagine picking parts out of a bin for 8 hours. That's your job. That's more or less unbearable, right? And that's honestly kind of the waste of a waste of brain power on a person. So automating dull, dumb tasks like that. I say dumb not in a bad way, but you know, the task itself requires very little. You can tune out and still do it, right? That automating that task lets you take a person and let them do something that adds more value to your organization. And again, you can't. It's hard to put this in a spreadsheet, but kind of from an intangible standpoint, the fact still remains. The less people you need to do these repetitive, dull tasks, the more capacity you have for more complex tasks that people actually are pretty good at. I'll pause again for just another quick question if anyone has one.
We've got another good question here, Manan. How would I interface a system like this to my machines?
Okay. So a very common answer to most questions in a presentation like this would be, it depends. And I'm sorry to say that's exactly what I have to say in this case. But it really depends on the interface of your particular machine. What kind of communication protocols can it handle? On our system, the component that would be interacting directly with your machine would be the robot. And on that side, we've got a pretty good degree of flexibility. It can handle Ethernet IP, TCP, Modbus, discrete digital I/O if that's what you want to do. There are many options. We can certainly talk about your specific situation. We'd be happy to do that. So thank you for that question. I'm sure that a lot of other people probably were wondering the same thing. Cool. Moving on. With that, let's talk about the top 5 reasons to bin pick. When your part presentation can't be changed upstream. I've had a lot of conversations where we say, okay, this is pretty straightforward, but my parts are dumping out in a bin upstream and it's an extruding machine or something, for example, and I can't really slow down the process, or for whatever reason I'm constrained upstream and I can't change how the parts are presented without having an intermediate step where someone literally just spends a bunch of time staging parts, right? Bin picking fits in really well there. When flexibility is more important than cycle time. I haven't talked about cycle time yet, so let me do that real quick. Cobots, like I said, are meant for mimicking human capabilities, right? So there are certain situations where you have a cycle time of like maybe a second or two. Not really a great ballpark for a cobot to be in. Every once in a while, your stars might align perfectly and you can get away with it, but in most cases, a good rule of thumb is 4 or 5 seconds for a collaborative robot. And actually, with the amount of data and numbers the camera needs to crunch every time it scans the bin, a couple seconds is good there too. So if you can afford anywhere from 1 to 4 seconds to figure out what the next pick is going to be, that's great. You can actually do things, you can be clever about programming it, like when the robot picks a part and moves out of the camera field of view to do whatever, the camera takes the part then, it cuts your cycle time significantly to do that. Main takeaway for point number 2 here is that if you need to be super consistent with your cycle time, so you know, I need my cycle time to be anywhere from 3.5 to 3.7 seconds, or even honestly 6.5 to 6.7 seconds, right? You're not going to get that tight of a window of cycle times with a bin picking system. Just because your part density could change, your part orientations could change, certain bins, even of the same part, could take another fraction of a second for the camera. You can certainly get within a window, but cycle time is not the something that we chase with the bin picking system. It can be optimized, but yeah, flexibility is the name of the game here. High part volumes. This kind of ties into part presentation upstream. The higher your part volume, the more, I mean, depending on your process, right? Higher the part volume, the less likely it is that you can afford the time to stage parts individually. So at the very least, vision becomes an attractive option, whether it's 2D or 3D with high part volumes. If your part volumes are high enough, the most cost-effective thing is just to dump them in a bin to feed them into your next process. That's where bin picking obviously really shines. Multiple SKUs, I've kind of talked about this. Each SKU mechanically would need probably custom tooling. One bin picking station can handle several. As we discussed earlier, there's not really, the upper limit's determined by really you, not technical limitation in a practical sense. High value parts, we'll talk about this in a little bit, but just with automation in general, if you have a $10 part that you're producing 10 of, you have a $1 part that you're producing 10 of, and you have the budget to automate one of those processes, which one of them pays for itself quicker? It's that $10 part, right? Because every part you complete is a bigger chunk of value that moves through WIP. So high value parts in general tend to pay for themselves very quickly, or it just in throughput, and especially so with bin picking. Sweet spots. So how I'm going to break this down is I'm going to go through a couple of process sweet spots and then industry sweet spots. Okay. So starting out with the processes, collaborative robot applications. Like I said, the cycle times of a cobot and a camera align pretty well already. Typically, in a lot, especially in applications like a simple pick and place or machine tending where you're just picking up parts, not saw blades, right? But like picking up parts and feeding it to a process. In a lot of cases, no guarding is required, which makes it, which not only makes the robot redeployable, but the bin picking system as well. Programming is a big one, and we get lost a lot of times in, I don't need to invest in a bunch of new safety like I would with another robot. Think about programming though, right? Bin picking is optimizing it requires a lot of really hands-on troubleshooting, debugging, looking at what's going on. If you have to negotiate a cage, right? So if you have an industrial robot, we'll say, and you're trying to bin pick with it, great. I mean, you might have faster cycle times. But anytime you want to see what's going on through the programming process, you got to open an interlock, right? Or some kind of guarding. Robot powers down. That's a safe way to do it. There's a lot of lag time in your programming that's just not really there with a collaborative robot, because the robot can be running when you're right next to it and you can see exactly what the robot's trying to do versus what you want it to do. So programming's easier, and it just translates. The system as a whole translates very well from how people bin pick. High volume with mixed products. So the kind of the rough cutoff I've put here is 3+ SKUs, and that specifically is the point where bowl feeding ceases to become cost effective over bin picking, right? 2 SKUs, okay, maybe you could make that work. When you get into 3 or more unique parts, buying individual bowl feeders for each part number you have looks uglier and uglier, right? So high volume with mixed product, your part presentation cost is going to be much, much lower if you can bin pick all of that with the same system versus, honestly, probably even nested trays if you have that many products. High volume gives you faster ROI. That's kind of coupled with throughput as well as labor costs. The robot will give you over time a much larger throughput just through sheer consistency. Repetitive high volume tasks present a greater risk of injury. How many of you guys type all day and now you have that pain along the back of your hand, right? Or I see this with design engineers that do a lot of 3D modeling. They're clicking the mouse and moving it around all day. All the tendons through here hurt, right? You're not even picking up parts. You're not even picking up, a fraction of an ounce. You're just moving repetitively. High volume means you have all that motion. The risk of repetitive motion injury is much higher for high volume processes. I think we've seen estimates of up to like 80K per instance of lost time repetitive motion injuries. So it's not present everywhere, but it is there, and when it happens, it can be a big savings to mitigate all that. And then again, people don't want to do dull tasks, and especially in the current job market, if they see something better that's even marginally better, employers are having a lot of trouble with finding good operators that will do something that's not the most pleasant thing to do, right? Kitting. Multiple bin recognition is something I haven't talked about. I've talked about multiple parts, but the underlying assumption so far has been, oh, I have one part here, and then one part over here, and then all the way on the other side of my plant, I have a different part, and I can roll the system up. Kitting involves multiple parts in the same location, right? So one of the really cool things you can do with our solution is you can actually have different parts in different bins in the same field of view of the camera. And the camera can take one snapshot and queue up multiple robot picks on multiple parts. Bin picking looks awesome really quickly in this scenario because, again, depending on the size of your kits, how many parts you have, bowl feeding might not be an option. But from a cycle time perspective, not needing to do a separate scan of each different part you have saves a lot of cycle time there, right? So needing only one camera snapshot to capture all three bins, recognize them, and then tell the robot exactly what to do across all of them really makes an attractive sweet spot. If you have this, feel free to give us a call. We'd love to talk to you. And then high value product. ROI and break-even points scale very rapidly with high value, like my $1 versus $10 part example. In almost all cases that I've looked at, it's been well worth the time to do bin picking or make that next level automation investment. And then another kind of bonus here with automation is that when you automate something, almost by definition, you make the process more consistent, right? That lets you iron out inconsistencies, which typically means your quality goes up, which typically means your waste goes down. Not automatically, but the consistency lets you tweak your process to decrease the waste. And for a high-value product, all this unnecessary waste can add up very quickly. So if you can automate your process, make it more consistent, waste less, it becomes an attractive option pretty quickly, right? Moving on to industries, medical devices, sweet spot for several reasons. They typically have high-value product. In my experience, it's a lot of manual processes, and a lot of times it's not that, if something's being assembled, it's not that the assembly process itself is super complex, but historically, for whatever reason, there hasn't been a lot of automation, and all the parts are presented on trays or bins or whatever. So each assembly process has multiple parts that need to be picked in an unstructured fashion. One of the bonuses for medical devices specifically, is that there's this huge emphasis on serialization and logging everything about your process. So if something happens out in the field, it can be traced back, I think like to the raw materials or something, right? Like to which batch of raw material this product was made from. So I'm sure you guys have found this to be the case. A lot of time and effort gets spent on, especially in a manual process, writing down serial numbers, batch size or batch number, lot number, whatever, right? Automation can do this seamlessly for you, and not only that, it greatly reduces the chance of some kind of data logging error being made, right? So that's kind of just a bonus, not necessarily for bin picking, but automation in general for medical. Plastics. I'll try to be tactful about this, okay? Most plastic manufacturing environments are not pleasant to be an operator in, right? They at least 90% of the ones I've been to are either hot, they run pretty hot throughout the day, they're humid, they smell like chemicals. There's noise everywhere. If your job is to load a mold, for example, you've got this giant machine clanking in and out in front of your face all day. This, especially with the high turnover that almost all manufacturers are experiencing, plastics are having a really tough time because it's not pleasant for anybody, right? And that's not so much a knock on the environment of a plastics plant. It's just that's just how plastic products tend to get made a lot of the time. On top of that, so you have high turnover. On top of that, most likely you've got lots and lots of unstructured parts all over the plant, right? Especially with things like extruding machines, because the heating and cooling of your product is super tightly controlled. If that machine stops for any reason, everything gums up, and you're looking at typically a day or more of downtime just to get that machine started back again. So you can't stop an extruder, which means you probably don't have the capability or the bandwidth to go stage parts from extruders as it comes out, right? Which means a lot of times they get just dumped into a bin of whatever size. Either a bin or kind of like a canted chute that just collects all the parts at an incline. Great opportunity for bin picking. Injection molding, a lot of times, you have a gantry robot that theoretically picks out injection molded parts and places them on a conveyor. Most times, the end effectors on those robots use suction cups, which wear out, and the drops become more inconsistent. The drops become earlier, right? So there's no real good way to predict exactly where that part or how that part's going to lie on a conveyor belt at any given moment, right? So you have at least some unpredictability there. A lot of times the conveyor belt just dumps the parts into a bin. So overmolding processes as well. Everyone that I've seen, it involves an operator with all the inserts or substrates in bins around the molding station, and they just pick one, place it into the mold, process happens, dumps into yet another bin. Overmolding opportunities ripe there. So plastics is, I've classified that as a sweet spot for many different reasons. There's just opportunities all over the place. Automotive tier 1, I'm not sure I need to spend too much time on this slide. I think automotive is a sweet spot for just automation in general. High volume, high value, high mix, all are a given. On top of that, automotive at the scale they operate, they tend to know processes very well. I would say that's one area where the engineer that designed the process probably knows as much as the operator. So with all that being said, I want to be honest with you guys. Where do you not want to use bin picking? I've said this a few times. If you need the cheapest possible automation solution, no matter what, bin picking probably is not the right candidate. Fast cycle times, again, under 4 seconds, probably not a great fit with a cobot, but also the camera itself has a multi-second cycle time for all but like the very simplest parts. And again, part complexity, especially lighting, if you have skylights and stuff everywhere and the lighting's not consistent, that could take some extra processing time. If your parts are partially oriented upstream, why do I say that? Not because it's a bad pick, no pun intended, not because bin picking's a bad option, but because something like 2D vision might actually be sufficient. Or you could do something clever with gravity feeding them that orients them perfectly. But I'm saying this is a sour spot because if your parts are at least partially oriented upstream, you may be able to do it more cost effectively. Small batch sizes, that's just kind of general automation. With the investment that the system requires, you want it to be running as often as possible, right? So if you have small batch sizes, the system might just be sitting idle. Unless you have many, many batches that get processed one after the other. Easily entangled parts, this is an important one. Okay, so say you manufacture mattress coil springs. Again, bin picking is super easy for people, right? But it's highly unlikely if you had a bin of springs in front of you that you could pick one out of the bin without another one being entangled in it. And even if you were limiting yourself to one hand like a robot, even if you shook the part, you can't repeatably get those parts detangled, right? So if your parts tend to get entangled easily, you probably don't want to bin pick them. I'll stop for another quick question. I know we're nearing the end of the presentation portion.
Yeah, we've got a good question on what parts can be picked, and can the system be used to recognize clear plastic parts?
Great question. What type of parts can the system pick? There's a certain size limitation, right? So our camera tends to handle much smaller parts than we've seen other cameras be able to handle. In general, there's no hard and fast answer to what type of parts can I pick. If you've got sheet metal parts, we can handle it. If you've got plastic parts, we can handle it. A lot of it depends on the end effector and how the system ties into your existing process or machine. Clear plastic parts can be problematic because at the end of the day, I mean, so our camera uses structured light, which in a nutshell depends on very heavily on how well the light is reflected back. Clear plastic tends to diffuse the light or refract it differently, so it's hard. Probably the best way to answer your question is that it's on a part by part basis, and the only way to really know is to send us your parts and we'll test it on the camera. And that's the case with honestly any vision system. You should never make a vision. I would say, in my opinion, you should never invest in a vision solution without actually running a test on the parts, regardless of what the specs are and how well your part fits them. Another great question. I actually wanted to say that bit about testing, but that question was a great opportunity to do that. All right, so moving on. Let's talk a little bit about our solution. So basically here you see it in action. We'll let it run throughout, but basically we have a collaborative robot and a Canon Vision system, the RV series, right? The collaborative robot, I probably don't need to tell you guys which robot this is. It's probably pretty obvious. But this has a 3, 5, or 10 kilogram payloads, depending on the size of the robot. There's a 3D camera control PC that you guys can't see because it's kind of tucked under the system to be more compact. And then one of the cool things is that this entire system is a mobile platform that is meant to be rolled to where you need, right? With the system, what's included is on-site installation, startup, training. Again, we like to be an extension of your engineering team. So if you need help, even designing the end-of-arm tooling or fingers or programming the system, we're happy to do any of that for you. The cobot, good rule of thumb for the different sizes of this, 3, 5, 10 kilogram payloads and the different reach. The smallest size is roughly equivalent to a person sitting at a workbench doing something. The mid-size is roughly equivalent to a person standing in one place and doing something. The largest size, 10 kilogram, 1300 millimeter reach is, imagine what I'm doing right now, walking around in a small area, maybe doing something with both hands, right? That's kind of the application tiers. The camera unit, like I said, I kind of let it slip a little bit, but the Canon RV series is what we have found to be the Cadillac of 3D camera units. We have successfully tested parts that other systems have not been able to, like thin parts. So if you have sheet metal plates, slender parts, shiny parts, on top of the clear plastic parts question, shiny parts tend to be a problem for vision systems in general. Matte black parts, because reflected light, matte black absorbs light. One cool option is that you can do consecutive picks, meaning the camera, between picks, the camera says, hey, did my bin actually change? Did the pile kind of collapse when I picked that last part? No? Okay, I know where my next part is. Robot, go ahead and pick it up. I'm not going to do the full 3D scan. So that's a great option to decrease your cycle times a little bit. And then, of course, the multiple part recognition, which I kind of geeked out about a little while ago. Why do they work so well together? Well, flexibility. This is something I haven't touched on, but this is kind of one of the insights we had when we were implementing this or integrating this. Cobots, one of the big benefits is that they are more a tool that you can use around your production facility rather than a dedicated piece of machinery. So really that gives you many more options to deploy it where needed rather than, basically it breaks the mindset of coupling something to one process day in and day out. So if you think of it as a tool, after your very first application, we find that customers immediately, the light bulbs start going off. Oh, I can move it there and do that. I can move it there and do that. Really where you need it. From a retrofit, we designed this from the ground up to be a retrofit to machines, not a work cell, right? We can bolt it onto a work cell, but the system isn't meant to just be its own big thing. It's a retrofit. And if your application doesn't require guarding with the collaborative robot, then it's a much easier retrofit. Overall, collaborative robot, I talked many times about how it's meant to mimic what people do or people capabilities. Overall, the system is very close to how a person would actually carry out the process. You can't program a person, but other than that, in general, you have vision and you have a pick, and the logic is largely the same. And then again, the cycle times of the cobot and then the camera system tend to line up pretty well. So you can do some pretty clever things with the programming by staggering when they both operate. We're nearing the end of the presentation, so I want to rush through these. Each of these has a bunch of questions. I'm not going to go through all of them. The presentation will be available online soon, so feel free to download it and view it at your leisure. But 4 things. So with the clear plastic parts, or for your specific application, we're going to start by asking you tons of questions, right? So these 4 categories of questions are kind of important. The more you know about these, the better off, the more quickly the conversation is going to progress. So parts, process, constraints, environment. How can your parts be gripped? How much do they weigh? That's on the engineering side. Also, how many SKUs do you have in production? What's the volume of each SKU, right? Even if you can't do all of them, can you do your highest volume SKUs with a bin picking solution? Process-wise, I won't even go into this, but I will say, get your operators involved. We've found that the earlier an operator is involved in the discussion, the more accurate information we actually have. Your engineer might be the one that designed the process or the piece of automation. Your operator is the one that says, hey, about every 15, 20 minutes, I have to hit this with a hammer, or everything kind of pauses. So all of that contributes to the robustness of your robot solution. And often really important little details are known only by the operator. So that's on the process side. Constraints, obviously, what are your cycle times? What is your desired payback period? What are your safety requirements? What's your burden? If I'm talking to you guys, I will ask you the burden rate at some point in the first conversation, guaranteed, because of the emphasis that I've seen on labor costs. And then environmental, as you can probably imagine, the camera requires a certain vertical height. If you have low ceilings, or you run production in a crawl space for some reason, all that is good to know early in the conversation. Ambient light, you have skylights that change the lighting, right? Are you misting water everywhere? So, last slide before we take a longer look at our demo. Key takeaways. So, as I've said up front, bin picking is not the easiest or cheapest solution. If you can manage, you should at least investigate bowl feeding, 2D vision, mechanical fixturing. Worth investigating before bin picking. The cost effectiveness of bin picking is realized really when you have 3 or more SKUs processed by the same robot, and your parts can't be staged upstream. That's kind of the first indicator that we look for when evaluating bin picking solutions. our bin picking platform, the CRP-BP, it's a tool. It's not a machine. And it's designed to directly replace manual picking. So roll it into place whenever, wherever you need it. And one thing I just want to make sure everyone knows that's seeing this, regardless of what problem you have, whatever part presentation option you need, Cross Robotics would love to help. If it's something that's outside of our wheelhouse, we certainly know somebody who can help you. So, that being said, I'm going to skip past the question slide here. I will take questions, but first of all, thank you everybody for attending the webinar. Really appreciate it. Gives me a lot more energy when I'm talking to you guys. So, yeah, right now I would be happy to see or happy to receive any other questions you guys have been sitting on, and our demo here will just kind of start. And real quick thing about the demo. So I mentioned part optimization takes a lot of effort, right? We did not fully optimize this solution because there's actually a couple of good talking points based on what we see here. So if something happens that's unexpected, I'll talk about it, okay? So that being said, questions?
Yeah, Mon, we have a number of really good questions that folks have asked. First off, how do I determine if a system like this will work for our applications?
I'm sorry, the last part was applications?
Yeah.
Okay. Talk to us about it. That's kind of the name of the game with robotics. Applications a lot of times seem very simple when you describe them to someone, but like I said, a lot of times in your actual production environment, little details get noticed that can change the scope of a project significantly. So unfortunately, but realistically, the answer is it depends what your application is, your cycle times, your parts, your payload, your materials, all that.
Great. We've got another question here. How would a system like this recover from a crash or a missed pick?
However you program it to. Error handling and recovery, I'm sure you guys probably know, anyone with experience in robotics, error handling and recovery can take 80 to 90% of the time you spend programming a robot, right? It's so easy. I mean, in 10 minutes, you can teach a robot to pick up a part and put it here, but what happens if someone bumps into it and faults the robot? And what happens if a light curtain gets broken? What happens if a part isn't there? There's all sorts of things you can do. Realistically, we would have, for part present specifically, you can incorporate sensors into the end-of-arm tool, like is available here, to detect, I've picked up a part, but are my jaws all the way in the closed position? Well, that means I missed the part, right? So I have a feeling a lot of the answers to these questions are going to be it depends, or it's very flexible. And if that happens, it merits further discussion. Feel free to reach out to us. I hope that answered the question, by the way, but really there's several avenues. But error handling and recovery certainly is a major component of any automation project.
Right, we've got a few more. Can you clarify what you meant by redeployable and how that would affect ROI?
Yeah. So redeployable means if you have one process, it's fairly simple to say you have multiple processes. All right, I'll try not to trip over myself by overcomplicating. If you have multiple processes, redeployable means you can take one system and tend both of them. Now, this is assuming this is something like a job shop situation where both processes wouldn't run at the exact same time. But if you have, unpredictable processes, one of the major challenges of automation, especially with like an industrial robot or a gantry-style system, is that if you get an industrial robot, it requires so much guarding and sometimes infrastructure. If your power requirements are, multi-phase or 480 volt or whatever. The demands of traditional automation are such that when you automate a process, that doesn't move, right? So if you put a robot next to a conveyor belt, it stays next to that conveyor belt. In a job shop, this makes it pretty difficult to pursue robotic automation, right? And I'm saying job shop specifically, but really I mean multiple processes. So redeployable means, hey, if I have these two processes, I don't need to choose one and couple whatever solution to one process, and then really I only get the gains component of my ROI when that process is active, which might not be all the time, right? So the way that redeployability contributes to ROI is that your system needs to stay idle for much less time, because if this process isn't active, you can redeploy it over here and you're still getting production out of a system.
Great, thank you. I have another question here. What are the typical safety requirements, if any, that will be needed?
We have found that in a lot of applications, an area scan. So like, let me take this system. By the way, observe the changeover. Safety. We've found that in a lot of systems like this one, you can get away with, by the way, this is Shunk's coax gripper. It's designed to have, generous radiuses, not no sharp corners or edges. One of the guidelines of collaborative design. But in a pretty simple application like this, we're not shooting flames from the end of the robot or spraying acid or cutting trees. The application hazard is pretty limited. Really, as long as no one gets hit in the face, it's fine for me to stand, right next to it. In this instance, if your risk assessment, we always say conduct a risk assessment. If your risk assessment deems that an area scanner is needed or the robot needs to pause when someone approaches it, just because you just want to avoid collisions altogether, what we see a lot of the time is a laser area scanner is sufficient for safety. Sometimes you might need light curtains. If you're my kind of tongue-in-cheek example of saw blades, if you're picking up saw blades with a robot, you'll probably need, your tooling's not hazardous, right? Probably a robot with a few suction cups on the end. But once you've picked up the part, your overall system is hazardous. So really it depends on a risk assessment. A lot of times, what you don't need with a collaborative robot every time is guarding. So in typical machine tending, pick and place applications, area scanner, light curtains, things like that. Even pressure pads are an option. A lot of applications we've deployed where the only safety measure was to make sure there, no walkways were obstructed and have an e-stop available outside the working envelope of the robot. But again,